Well, let's begin with the Compton and photoelectric. They are, it's interesting you picked up that similarity. They are rather analogous processes. Wow, this is amazing. The Compton effect is where you shoot in. Typically, you have to use X-rays because the change in the way, what it is, of course, is you shine in a wave with a certain frequency and wavelength. F lambda is equal to C, electromagnetic wave. It strikes usually an electron, which is more or less at rest. Well, you know, this is actually being recorded, I realize, so it's going to be webcast. Maybe I can just put this in a different place. How's that? That's still not good. Wow. Right now it seems to be. It's just amazing. Okay. Well, let's see if it works, sort of. Okay, so the idea is that you shine in this wave. It hits an electron that's normally attached. I think, as I recall, Compton actually used carbon, maybe graphite. And he observed a wave coming off with a wavelength that had gone down. Oh, actually, no, the wavelength actually increased. The frequency had gone down, maintaining the fact that the frequency times the wavelength is still C. Now, you do get an electron coming off, so that's the similarity that you picked up with the photoelectric effect. But they don't use this to really determine like wave work functions. Just used mostly to test the idea that the incoming X-ray could be treated as a photon, having a frequency and an energy proportional to its frequency. So that's the thinking behind that experiment, just to verify that the energy of that photon is h times the frequency, and that it has momentum equal to its energy over the speed of light, that it's behaving like a particle, because you could treat the scattering process like as though the electrical, like a billiard ball. You have one particle coming in, bouncing off another particle, and you could just go back to 8A and conserve energy and momentum. And those things worked out. In those years, 1924 or so, this was very controversial. In fact, there was a competing theory by some brilliant men, Bohr among them, a man by the name of Slater, and another great physicist, I think, was in on yet another theory that was much more. In those, it's really kind of funny. In those years, they were so challenged that they were willing to throw away the conservation of energy, anything, just to make things work. And they had come up with this opposing theory. But when Compton did this and showed that no, it's not that complicated. You don't have to give up conservation of energy. Just say that energy is proportional to the frequency. The incoming wave has momentum, and you can calculate everything on just those bases, and it's fine. Now, the photoelectric effect is a similar thing, you're right, but it's used somehow in different mode. Namely, you have a particle held in a potential well, as it were. You can even draw a well like this. The electron happens to be in one of its levels, highest level, and there may be other levels that are occupied by any number of electrons, depending on the stuff. And you shine in, again, you use the idea that it has that much energy. All that energy is absorbed in one contact with one electron, which then is ejected from the material, leaving, it needs that much energy to climb out of the well, right? And as a work function, or as it's sometimes called and it comes out with the residual amount of energy as kinetic energy. So it's kind of very similar in principle. You're right. It's a very keen observation. But it's sort of used in different things. We use this for, first of all, usually you don't use X-rays. Oh, you could actually. But if you shot it in an X-ray, it could actually lift an electron out of a very deep level. And so you can do X-ray spectroscopy and get a photoelectric effect. And that is done. That's a whole field of physics that's, as I think may have mentioned, that goes on actually at our lab here. Because they can generate X-rays in abundance, and you can actually do spectroscopy of these deep levels and lift the thing kilovolts of energy if you put in a kilovolt X-ray. So there's a similarity, but it's a kind of different spirit involved only. Yes?
So for the Compton effect, the photon is hitting the atom, the nuclear proton, right? And the one on the other side is hitting onto the electron instead. So they're hitting different things.
Yeah, the picture is sort of simplified. This is a material over here. That's probably a carbon atom. So in a way, it's similar, as he said, as he noticed. This could be carbon over here too. Could be graphite or diamond or what have you. And in principle, again, the principle is the same. He's really hit it. The principle is the same. You shine in an energy as a wave. The electron absorbs it and is knocked out in this direction here, say, and it's ejected from the material. And in fact, I think they, later on after Compton, they actually observed those eject electrons. They were doing the photoelectric effect. But I guess they went even further than the simple photoelectric effect, where they actually measured the angle at which the, I think they call that angle phi, and they call this one theta in the literature. They actually measured the angle just to be sure that the energy result and momentum was conserved. So you could actually do it in great detail. They don't bother usually with the photoelectric effect, for example, could be used as a motion detector. You know, you have a beam of light, and when it's interrupted, you get a change in the current being generated by a photoelectric. Did you ever see these things? You know, the motion detectors of trip wires, as it were. Yes. And energy, yes. Well, in order to calculate the angle that the X-ray comes off, that involves a certain momentum forward, and you'll have a certain moment. You'll have a wave coming off. He measured the angle of the outgoing X-ray, and he measured the wavelength of the outgoing X-ray. So he knew angle and this. So he has to conserve momentum in this direction. I don't know exactly. Without knowing exactly where that went, well, apparently it's enough. If you know this angle and you know the shift here, you know how much energy was carried off by this electron. So maybe you don't have to know that much more about this electron. At least Compton didn't know it at the time. And you could just count up the momentum going in, namely HF over C. You come out, you know the momentum and the angle coming out, HF prime over C. And the angle, and apparently that's enough. It may actually be worked out in your text, how you do that. It's relativistic, actually, because these are pretty high energies. But it's straightforward energy and momentum conservation, a billiard ball thing, and it was just used to verify that these ideas work. And at the time, it was a major breakthrough because it shut down that other theory, which was complicated and said, I can't even repeat it. It's just a cooked up theory to try to help them understand this. And if it fooled Bohr and another American named Slater, who was later a professor at MIT, brilliant guy, and they had concocted this theory, and they gave it up. When Compton came up with it, they said, okay, you're right. And you just treat them as billiard balls, and it works out nicely. So I hope that's enough on that. Well, these two ideas are similar. What we mean by an R-dependent wave function, now it works mostly with the hydrogen atom or atoms, where you know that the electrons are somehow attracted to the nuclei, and you have a wave function which has, turns out, because it's an atom in three dimensions, you have to treat it in three-dimensional form. And the three dimensions that are easiest to work with in this kind of geometry are a radial part. I think I've mentioned this before. So at a given point here, if you want to specify that point, you could give it x, y, z coordinates. But if you're in spherical coordinates or spherical type of problem, it's easier to refer to its radius, its angle from some particular direction, usually called z, and that angle is called theta. And then you project this onto the xy plane. You project that position point, and you describe yet another angle phi. So those are the three coordinates that give you three dimensions or specify a point. So it's not so familiar to us, unless you remember your calculus, where I'm sure they had problems like this in calculus, where you would work in spherical coordinates. But in any case, it turns out that there's a function that depends on R, a function that depends on theta, and there's a function that depends on phi, the angle phi, and they all separate. So what we mean by a radial eigenfunction, it's that part of the wave function which varies in the direction R. In other words, if you go outward from R, along the direction R, outward, the wave function could sort of start dense at the center and move out and perhaps have nodes. But they're varying in the direction R. And you can plot that, this R function, as saying I start at the nucleus, where R is 0, and I just plot the amplitude of this wave function as a function of my distance from the center. So I have this spherical object, and it has a wave function which varies as they go outward in R. So we speak of that as the R-dependent eigenfunction or wave function. And as well, it may depend on the angle that you have, which gives it a shape in this direction. Sometimes it's spherical, and sometimes it doesn't vary in that theta direction. Those would be called S-states. See, if there's this theta thing, if there's no angle dependence, those are called S-states. So that means that the wave function goes out and it doesn't vary in that direction. So just to answer your question, it's just that some things, atoms have these radial wave functions which vary, and I was hoping that you would use the simple rules, which we're going to apply in the next part of this question, that the wave function very orderly way. The first one has no crossings. So this would be the first level. The second one has one crossing, one node, as Schrödinger said, that he can get integers out of this by the number of nodes, like a standing wave of a string. So that the second wave function would have one crossing. So, and you see, what this is saying is that as I come out in the radial direction, I have something at the center. It goes down below zero, and it can be sort of negative here. So that state would look like that I drew there, blue one. It goes below, it crosses so that there's a zero probability at that point, and it goes actually negative here. Negative has some meaning, because you can, like waves, you can add pluses and minuses and get cancellations and so on. So negative has a meaning, but can you see this sort of variation as they go out at R? It's going from something at R equals zero. Let me try to do it this way. R equals zero. You have something here. The wave actually goes negative, whatever that means. For matter, but it means something. And then it goes negative, and it doesn't come back up to zero in that next site, in this one. Okay? And then, again, I'm just using the rules that every more excited, higher energy state has one more crossing. So the third one would, again, cross the axis, maybe further out, and would cross the axis a second time before it dies out. So this would be the third state, which is saying that radially, as it's going out, it crosses, but then it comes back up and goes back down. So that's what we mean by a radial eigenfunction. These are the functions that give you energies that actually fit into this particular shape. As we talked about, I guess, the last two times, you're trying to fit waves into a certain shape. Here you're trying to fit it into an attractive Coulomb potential energy. And these are the kind of shapes that fit into that. So those are the radial ones. We could talk about the angular ones, but that's rather more complicated. A little more complicated, not a big deal. Complicated. Okay, now that flows very naturally into the question that you asked about strange-looking potentials. I don't know which one in particular. Oh, it was a triangular one, huh? Like this, huh? And did this say it went to infinity? And presumably that one's going to go to infinity too. Did it sort of go like this?
Yeah.
Oh, okay. That's fine.
And that side is finite as well.
This side's finite too? At the same height?
Yes.
Okay. That's fine. We can handle we can do anything. I reminded a joke. There was once a theorist who gave a talk, and he said, and somebody asked him, "Can your theory explain everything?" He says, "My theory can explain anything." And I think that's almost bad if you can explain anything. That means right or wrong, you're okay. In any case, no. So there are various rules simple rules that we have to dealing with these things. First of all is the idea that as the energy, so look, what this is this is a well, and the electron is actually sort of, or the particle is bouncing back and forth in this well, and the idea is we have to be able to fit the way there's a quantum condition which says various things. Namely, for example, the first wave must have, as I drew over there, the smallest number of wiggles. So the first wave must look like that. Now this is a finite value, so the first thing is smallest number of wiggles. I don't know, this is highly technical terminology, the number of wiggles, or the number of crossings, if you will. The number of times this wave function crosses the axis is 0. Okay? The number of crossings is 0 for the lowest one. And then you just go up in the number of wiggles or the number of crossings. So that's the first rule. So that would say the next one I have to have more wiggles and I have one more crossing. So that necessarily is what the second one will look like. Can you speak up a little? That's a good point. You're asking about the spacings. Now, this kind of pictorial analysis is just qualitative. So you really don't get quantitative spacings out of it. You can make some educated guesses about that, but we won't get specific answers. I'll never ask you, and a problem like this, to give me specific answers. Although there are books, I think I actually quoted something in my PowerPoint, where somebody's worked out something like this mathematically and could give you the energy level value. But I wouldn't ask you, in a case like this, it's way beyond this level to ask for the specific thing. But I want you to have a feeling, just for the idea, that these are waves, just trying to fit into a shape. And there'll be certain characteristics that it will have. And if you can do that, I think that's terrific. Because it's better than thinking, oh, there's some kind of mysterious thing going on. It's not mysterious. It's just waves trying to fit in a box of various shapes. And these necessarily would be the way those shapes would be. And if you looked up some mathematical solution, they'll give you a fancy formula and it'll just say this. But it will give you the energy. See, that's the difference. It'll actually give you a quantitative, which is important, because you want to know how much energy do I need to go from there to there, say. If you really wanted to do it carefully, if you want to know the spectrum of absorption and emission. But I won't ask you that. If I give you a problem like this, it's too hard to do. I mean, you'd have to sit down and work for a week to get the answer. But the first thing is this idea that the number of wiggles goes up as you go up higher in energy. So you definitely know that this is the first energy, and this one will be greater. E2 will be greater than E1. Why? Because the wavelength is shorter, and the energy, although an electron moving, is p squared over 2m, and p is h over lambda squared over 2m. Or you could even do it like this, 1 over 2m, and put lambda is, let's see, so lambda is c over f. So it's c over f squared. So you can see, well, it depends how you want to look at it, but there's all kinds of ways. But the shorter wavelength means higher energy. This is a kinetic energy. So that's what we're using. That's the idea we're using. So that definitely the waves will get shorter because the ball is just moving faster in the box. And that will be the energy, if you ever measure an energy of a ball in such a box, you'll either get this energy or that or another, because those are the ones it can live in. Those are the shells on which it exists. The energy levels. As you said, we don't know exactly what they are from this analysis, but you can be sure. Yeah. Well, that's only for the square box. Yeah, this won't be anything quite like that. Sort of similar. But you see, this one is kind of a mixture. You're going to get something that if we were to guess, but again, using intuition, what you said is very perfect. Mainly in the square box, the energies go up to 0. The next one is 1, is 0, But the other principle that I wanted you to know, the second principle, is that in a finite wall, there is tunneling. Now that goes to another question. What is tunneling? Finite wall, the particle doesn't stop at the wall. Because it's a wave, this particle leaks into the wall a little bit. That's a tunneling effect. You see, this is a wall. It's like if I would have a ball, throw it against the ball would stop at the wall and come back. But in a wave, there's a finite probability that just behind the ball of it's come through. And that's represented by the fact that this wave function has some amplitude inside the wall. So in a finite wall, but in an infinite wall, on the other hand, the particle has no chance of getting through. So if the wall were infinite, if the problem was set this way, this way, yeah. I'm going to infinity. That's why I asked you, let's go to infinity. If it goes to infinity, the particle does not tunnel. So it would look like that wall is immediately infinite. It does not tunnel at all at that point. On the other hand, here, it's reaching a finite potential. This is the potential there. So here it would tunnel a little bit. Because this is finite. This comes under the characterization of finite wall. So it would tunnel a little bit here. So the wave functions in this case would look like the next one would be a higher one, and it would tunnel a little bit into this side. That's the second one. I want you to just understand the principles behind it. They all kind of are logical too. There really isn't just rote memory. I'll show you what the rote memory. Yes?
Sorry, did you draw infinity wall?
Yeah, it's infinite way up here. In other words, if I had to go this far, if I went this far out, because this is spatial dimension. So this is a wall that looks like, or it's like a trench. It's more like this. And what is a trench? So I throw the ball in here, bouncing back and forth between these walls. The next higher level, if I threw it at higher speed, it's going to bounce back and forth in a higher level, at a higher energy. It's just bouncing back between these walls. But this wall here is not quite infinite yet. It's infinite out there, but it's not infinite here. So that's why it dies out immediately at this wall. And it trails off a little bit into this finite wall. Because that wall can climb up this wall, but it can't climb up this wall.
And so it's the angle that
It's the yeah. In other words, what this is trying to represent is a sloping hill. So the ball can reach the sloping hill, and this is the total potential of that hill at that point of distance x, say, in this direction. And the potential increases. The potential increases as you go further and further up. Right? It's harder and harder to climb up there. Now, these are wonderful questions. This is really what we should have, the guts of the thing we should have been talking about in the class that we had over the time. Yes?
So, what happens when you also said when you don't have the like say you have like half the square love, well over here too, then you don't have the confinement of the number of possibles. As long as on the infinite side you're at 0, right when it hits the wall.
The infinite side, when it hits the wall, it doesn't go into the wall.
Right.
And then what do you want to go on the other side?
So the other side there's no wall. There's like
Oh, no wall at all?
Yeah.
Oh.
It just gives you like the energy levels. So
Oh,
like the wave just
that's also a very fun question. You have to get these confinement things. The wave function has to be confined at both ends. So if you're talking about this, say, fact, this room is sort of like that. See, we have a wall here, and we have a slope up here, stairs. So we have kind of like that one over there. And the question is, if I threw a ball against this wall, how far, at a certain speed, it would hit the wall, and it would roll up a certain number of steps, and then it would roll back down. That's the cyclic motion that is trapped. That's this story. So here are the steps. Oh, I wish I thought of that. Yeah. So if I throw a ball with a certain speed, it'll roll a certain way up. Suppose it was a ramp, if we go smoothly. And then it would roll back, and it would do something like this. But in a room like this, there would only be finite energies, where in a quantum system. Right. So that's the picture we have. Now, she said,
So it's infinite on one side.
infinite over here, but I want to make it flat here.
Yeah. No.
Now I have, yeah. That's a very good question. And who's anybody going to guess?
So what I thought was, if the energy levels would get if you're at zero on the infinite side, and then you just
Certainly zero here.
forever.
Yes, they will go on forever. And moreover, they're not quantized. Because there's nothing forcing them to have a condition at both ends. So that means it could have anything at this end. So in this case, you don't have quantization. You have to have cyclic motion. And if this room were perfectly flat out to infinity, I could throw the ball against this wall and it would just keep going forever and never come back. And then I could throw the ball with a little more speed, and it would just hit the wall a little harder and come over with that. So what you get the energy levels in that case, very good question, would be everything. You could have any energy you want, and there's no quantization because it would die here, yes, but there would be no quantized level. You could have every possible energy because it's not cyclic. It's not coming back and forth. Because I'm not confining the wave to do something at this end. So it can do anything. It can have any wavelength it wants. So that you have no quantization. And so the waves can have any wavelength, and can have any momentum, and any energy. That's a very good point. And in fact, even in a case like this, if you put in an electron with enough energy to ride up here, it will not be quantized either. And what you get is the third rule is that the wavelength depends on the one over the wavelength depends on the energy. So that, for example, what will happen here is that it's rolling along, and then it falls into the well, sort of like somebody came in, rolled the ball on the topmost stair. So it's rolling along, and then it falls into the well. So it goes down the stairs, picks up speed. Picks up speed means it's going faster, means its wavelength gets shorter. So its wavelength should get shorter. That means it's falling down in here, but as it rolls back up, its wavelength should get longer. Until it rolls back out, which it could. The ball could start on the top level, roll down, hit the wall, bounce off the wall, not lose any speed, bounce back up, go back up onto that level. But what it's done is it's moving slowly, roll down the stairs, pick up speed, hit the wall, bounce back up, we're assuming no loss. Goes back up there and continues on its merry way. And that will all be represented by it's going along in a long wavelength, meaning it's going slow. Here it's going fast. When it falls, if for example, it started, I guess it depends which way you're doing it. I have a picture starting up at the upper level, falling down the stairs, hit the wall, bounce back, and come back up. Well, if it was fast enough, if it hit the wall with a very high energy, it could hit straight back up and continue. So the wavelength would be restored, but it'd be long, because that means it's going slow again. And it goes faster, it picks up speed, it means the wavelength gets shorter as it's falling, and then when it bounces back up, it's going slowly again. You see that? I mean,
I don't understand what's happening that makes it go faster in magnitude. Because I don't understand.
yeah. It all goes back to the drawing. When a thing is going faster, its wavelength gets shorter.
Right.
Okay. So, suppose I roll the ball along through the door, I get to the top of the stairs, and it rolls down the stairs. Think of it as not losing any energy. It's just picking up. It's like it's falling on the movement. No resistance. It picks up speed. Right? If it's going faster, its wavelength is shorter. So you want to keep the wavelength. The wavelength is h over t. So which is h over mv. So as the v gets larger, the wavelength gets shorter. So as this thing picks up speed, let's say it's falling, picks up speed, so its wavelength starts out long, and as it runs through, its wavelength gets shorter and shorter as it picks up speed. In other words, represent the speed by a shorter wavelength. So as it's going down, it's picking up speed, so its wavelength should get shorter and shorter. It's the same argument as all of these. Here's a low energy, a low speed, and the wavelength is long. Here's a higher speed. This is a part of the constant at a higher speed in the box, and its wavelength is short. And it could be a continuous process. In this case, as I slide down, I pick up speed, and my wavelength gets shorter. Yes?
So with the instance where there's only one side of the infinite well,
Yeah.
and there's no quantization, why would one wavelength that's higher than the other have like why do they all have different wavelengths? Because even if it is there is no other side to the well, does this make sense? Why would it be like different even at higher energy levels?
It's a good idea. So let's pretend that we just have a wall. We have an infinite football field forever, flat. So I can throw the ball against the wall at any speed. If I throw it slowly, quantum mechanically, it'll have a long wavelength. If I throw it harder, it'll have a different wavelength, depending on how fast it's going.
Yeah. So
And I can make that speed anything I want, because I'm not confining it on both ends.
Well, wouldn't it still have, even though it's not confined, wouldn't it still have specific energy?
No. I can pick anything I want because there's something confining in this end, but it doesn't, the way this thing is confined is that if there is a confinement at both ends, because I'm forcing it into a certain space, but if the other space is free, I can make anything I want. Very, very important point to realize, yes. Yeah, so that's known as a free particle, namely that one that is really not bound at both ends. It's not confined. And it doesn't have cyclic motion because it's not coming back. Once it hits the wall, we're saying it'll go on forever, and there's nothing to force it to have any particular thing. It's a very, very good point. Yes. Yeah, and she was wondering, why is it quantized if I only have one wall? Why don't we suddenly quantization go away? Quantization only occurs in cyclic motion. And if it hits the wall and goes on forever, it's not cyclic. It's not coming back. If there's nothing at the other end. So you have to be inside a box of some sort. Or, actually, yeah, you have to be inside a box of some sort. Even an atom is a kind of a box. Because even if it's a hydrogen atom Does that make sense?
So, what determines what's happening when you're above the wall? What determines exactly what happens at that boundary? Like, how do you know?
Is that over here?
Yeah,
Or
like
here?
on the top. So if you
Oh.
go from the long wave lead to the short wave.
Yeah. So my picture is starting from the long way, starting from this side. I'm sort of like coming through the door on that upper level there, and I'm rolling along slowly.
So how do you know, I guess, is it easier if you're always at the bottom of like, the wave trough?
How do I know that one?
When you get to the edge of the well, is it always going to be like that, or can you be at the top of the wave when you get to the edge of the well? Like, does it make a difference as long as you're like speed up over the well?
Well, I'm not quite clear on the question. See, I'm just thinking of it this way. I'm a particle. I come in through that door on the upper level with a little bit of speed. I reach the edge of the stairways. Let's think of it as a smooth ramp with no loss. I roll down. I come down. I'll come this way. I'm sorry.
I think I can clarify my question. So when you reach the edge of the wave and you're above, yeah,
Right here.
on the other side.
Here.
Is it this way?
So this is so I'm against this wall here.
Yeah. So you can reach that edge at any point in your wave cycle, right? If you're on the top, you're above the
I'm above the, yeah. Then this would be a finite wall. In other words, this would be a wall, say, that came up to this point here. Let's say to the screen. Let's say the wall was higher than. In fact, this is the case. If I have started with the ball, let me do that case. Maybe this will illustrate the point for you. Let me have. This is the length of the screen. Now, suppose this wall really just was this high. In other words, it's not as high as the place where we walked in, up there. So this is where we walked in. Here's the doors. And here's the wall that only goes up this high. Now, if I introduce the ball at that wall up there, at that point, it rolls down the stairs, or whatever, and it reaches this wall. It's got so much speed that it can actually go up over this wall, and go over this point, classically. Because look, it started there. It's like if I had a trough like this, and I roll the ball down. If I have no losses, it had this much potential energy, picks up speed, and it'll come out faster, won't it? Do we agree on that? So that we just want to translate that classical idea into waves. I start out with a certain speed, slow here, and fastest at the bottom, because I've picked up all my speed. And then I roll back up, so I give back some of that as potential energy. And I come out here, well, slow, but faster than here.
Okay. So the wavelength is shorter.
So here my wavelength is long, here my wavelength is short, and here my wavelength gets sort of in between. Because I'm between that fastest speed and that slowest speed. Make sense? That's basically it. So you can just draw the picture. So if I were drawing this one, I have a slow speed. Then it gets faster. I mean, it's slow, but it gets faster. Then when I'm climbing back up, it's slowing down, so it goes fast, gets longer. And if I can get out, it's long again, but it's not as long as that, because this is faster than here. Does that make sense? That's what's happening. That's exactly what's happening. Yes, go ahead. This is really fun. I mean, this is so nice because you have a classical picture and you can rely on your intuition there pretty well. And we're just translating it into the idea that fast things have short wavelengths, slow things have long wavelengths, and as it goes from slow to fast,